In the last video, we talked about complex numbers. Once we have some basic understanding about complex numbers and why we are using them, it becomes relatively straightforward to talk about impedance and everything that's related to those concepts. For an ordinary resistor with a resistance R, the relation between the voltage across it and the current flowing through it is just given by this very famous Ohm's law, which basically just states that the voltage across it is proportional to the current flowing through it, and the constant of proportionality is given by the resistance R. And we have looked at this particular equation in video 18, right? And it's called Ohm's law. If we divide the voltage by the current, we obtain the resistance R, and the unit is volt over amp, and it has a specific name known as ohm, right? So the unit of a resistance is ohm. For capacitors and inductors, we know that the relations between voltage and the current are more complicated than this linear relation. In fact, they involve temporal derivatives. So the question is, if we can generalize Ohm's law to include capacitors and inductors and other types of components by using complex numbers, actually. So let's look at the capacitor first, right? In video 18, we gave the current voltage relation for a capacitor. The current flowing through it is proportional to the temporal rate of change of the voltage across it, with the constant of proportionality given by the capacitance C. Now suppose the voltage E is given by this complex exponential that we saw at the end of the last video. So from the last slide of the last video, we know that a sinusoidal voltage or current can be expressed using such complex exponentials from the Euler's equations, which was a result from the Euler's equation. So here t is time, right, and omega is the angular frequency, right? So the sinusoidal function or the AC current or AC voltage associated with this particular complex exponential has an angular frequency of omega, right? So in the US, this angular frequency is going to be 60 Hertz multiplying 2 pi. Outside the US, this angular frequency is going to be 50 Hertz times 2 pi, right? So this kind of AC voltage is going to be either a sine or cosine of this sine omega t or cosine omega t, and either of them can be expressed as a combination of these kind of complex exponentials. And in last video, we talked about how to use these complex exponentials to represent those sine and cosines, right? So here we are just assuming that the voltage equals to one of those complex exponentials, e to the j omega t, right? Now we can carry out the temporal derivative on this complex exponential, and we obtain an explicit expression for the current, which is also in terms of the same complex exponential e to the j omega t, actually, right? Remember that e to the j omega t equals to the voltage, right? So this term can be replaced by the voltage, right? We can just use voltage here. So the current IT actually equals to the voltage multiplying j omega c, right? The angular frequency omega and the capacitance c are real numbers, so they are just the scaling vectors. They don't really change the angle, right? They don't really rotate the voltage vector in the complex plane, right? But the multiplication by the imaginary unit j is equivalent to counterclockwise rotation by 90 degrees. which was one of the results we obtained in the last video, right? So if we look at the current and voltage, for example, at time equals to 0, so t equals to 0, right? When t equals to 0, this complex exponential equals to 1, which is unity, right? Then the voltage E at time 0, the voltage equals to 1. So the voltage is unity on the real axis. That's the voltage, right? And at this time, the current becomes 1 multiplying omega Cj, right? Which is actually a vector on the imaginary axis, and is 90 degrees counterclockwise from the voltage. And if we examine any other time points at which the voltage is not unity anymore, right? If we look at a time that's not 0, right, then the voltage is not unity anymore. It's a complex number that's given by e to the j omega t, right? It's a general complex number that's not lying on the real axis anymore. But it's okay, right? This multiplication by j will always put the current 90 degrees counterclockwise from the voltage. A counterclockwise rotation is called a lead. So for a capacitor, we say that the current leads the voltage by 90 degrees. For a resistor, the resistance is obtained by dividing the voltage by the current. And here, if we also divide the voltage by the current, we obtain a complex number. So voltage equals to e to the j omega t, right? The current equals to Cj omega e to the j omega t. And e to the j omega t and e to the j omega t can be cancelled out. So what we have obtained is that the voltage over current equals to 1 over j omega c. This complex number also has a unit of volt over amp, because it's voltage divided by current. We know that volt over amp is a ohm, right? So this new complex number, voltage divided by current, has the same kind of unit as the resistance, right? And this new complex number, 1 over j omega c, actually resembles the resistance of a resistor, and we call it the impedance of the capacitor, and we assign a symbol to it. That's Z subscript C. Right? That's called the impedance of the capacitor, and it has exactly the same unit as the resistance of a resistor, which is ohm. But unlike the resistance R, which is a real number and does not depend upon omega, the frequency, right? The impedance of a capacitor is a complex number because it has j in it, the imaginary unit j in it, and it also depends upon frequency omega. It actually depends upon the frequency of the voltage, right? The voltage across it. So now let's look at the inductor. For the inductor, the current voltage relation is also given in video 18, right? And the voltage across the inductor is proportional to the temporal rate of change of the current flowing through it. And the constant of proportionality is given by the inductance L, capital L, right? Now if we assume that the current has the form of this complex exponential, right, we can obtain the voltage expressed in terms of the same complex exponential, which is L times imaginary unit J, and then angular frequency omega, and then multiplying the current, e to the j omega t. Right? And then if we examine the time point t equals to 0, for example, right? At t equals to 0, time equals 0, the current I is unity and lies on the real axis. Right? That's the current vector. And the voltage is J times omega times capital L. Right? This one, the voltage actually lies on the imaginary axis. That's the vertical vector here. In fact, for every time point, the current I is always 90 degrees clockwise from the voltage. And in this case, we say that for the inductor, the current lags the voltage by 90 degrees. Again, if we divide the voltage by the current, so the voltage equals to Lj omega e to the j omega t, and the current equals to e to the j omega t. So e to the j omega t cancels out. Right? We obtain j omega capital L. So the division between voltage and current is another complex number, that's j times omega times the inductance L. Right? And this new complex number is what we call the impedance of the inductor, and we have a symbol assigned to it called Z, capital Z subscript capital L. Right? And it also has a unit of ohm because it's also volt over amp. Right? So now we can summarize our analysis for all three types of passive components. For the resistor, the impedance is identical to the resistance R. Right? For the capacitor, after doing some complex algebra, right, we can write that, so 1 is replaced with minus j squared. We know j squared equals to minus 1, right? So minus 1 equals to capital 1. So 1 can be replaced by minus j squared. Right? And then j and j cancels out. What we have obtained is minus j multiply 1 over omega c. So if we introduce the definition of the so-called capacitive reactance, capital X subscript c, which equals to 1 over omega c, right? Then the impedance ZC equals to minus j times the capacitive reactance XC. Right? And it is a complex number, and every complex number has a length, which is the distance to the origin on the complex plane, and an angle, right? So for the capacitor, the impedance has a length given by XC. And it also has an angle, right? Because it has a multiplication to minus j, and the angle is minus 90 degrees. Right? It lies on the imaginary axis. Right? For the inductor, we can introduce the so-called inductive reactance XL, which equals to omega times L, right? And then the impedance for the inductor equals to J times XL. Right? It is also a complex number. Its length is given by XL, and its angle is 90 degrees because of this multiplication of J. Right? And at this point, we have effectively generalized the Ohm's law because the impedance is obtained by dividing the voltage by the current. So the voltage E equals to the current I multiplying the impedance Z. And we can call this relation the generalized Ohm's law. And sometimes people just neglect the generalized and still call it the Ohm's law, but it doesn't really matter. So we can use the impedance just like the resistance. Unlike the resistance, the impedance for the capacitor and the inductor are frequency dependent. So let's look at how the length of the impedance, the size of the impedance varies with frequency for the three different types of components. So the frequency, we look at the frequency, and it's going to vary from 0, which is a so-called direct current or DC circuit. Right? It's going to vary from, the frequency is going to vary from the DC circuit to low frequency, to high frequency, and eventually to infinity. Right? So for the resistor, the impedance is the resistance, and it doesn't depend upon frequency. So it is R for all 4 situations. Right? for the capacitor, at zero frequency or DC in the DC circuit, the length of the impedance is given by 1 over omega c, right? So at zero frequency, 1 over omega c, omega is 0, right? So 1 over omega c becomes infinity, right? So the impedance of the capacitor is effectively infinity, which tells us that in the DC circuit, the capacitor effectively behaves like a break in the circuit. And we say it is an open. Right? It's a jargon in electrical engineering. It's if you have an infinite impedance, it's just like cutting the circuit at that point. Right? You're not sort of connecting the circuit. Right? So at that particular point, so it's an open. Right? And then at lower frequencies, 1 over omega c, frequency is low, right? So 1 over omega c is large, and the impedance is high. And then at high frequencies, the impedance is low. And at the infinite frequency, so if the frequency is infinite, omega is infinite, then 1 over omega is 0. So the impedance becomes 0, in which case the capacitor behaves just like an ordinary copper wire with almost no resistance. And we say it is a short. Again, it's a jargon in the electrical engineering community. So when we say something is a short, it means that it has almost no impedance. Right? And for the inductor, the situation is kind of the opposite. So at the zero frequency, or in the DC circuit, the inductor has an impedance of 0, and it behaves like a short. Right? And at lower frequency, the impedance is low, while at the higher frequency, the impedance is high. And at the infinite frequency, the inductor behaves like a break in the circuit. So it becomes an open. Right? After we are equipped with some basic understandings of impedance, let's talk about how current and voltage behave inside a circuit. We are particularly interested in how current and voltage behave in two types of junctions. The current junctions, which are nodes in a circuit, and then the voltage junctions, which are loops in a circuit. So let's look at an example given by these two resistors connected in parallel to a voltage source, right, in this particular very simple circuit. Right? So examples of current junctions or nodes are these two black dots. And at the first black dot, the current I is split into two branches, I1 and I2. Right? And at the second black dot, the branches I1 and I2 are combined into the current I. Right? So these two black dots are examples of the so-called current junctions or nodes. And then let's look at the examples of the voltage junctions, which are loops. Right? In this particular circuit, there are actually 3 loops inside of this circuit. Right? The first one let's look at is the the loop indicated by the blue lines. Right? So the current actually goes out of this voltage source, right? And then at this junction goes down, and then pass through this lower resistor, right? And then at this junction goes into the main current I, and then comes back to the voltage source. That's this loop indicated by this blue line, right? And then we have another loop that goes along this red line, right? This time it's not going sort of down to the lower resistor, it goes up to the through the upper resistor, and then comes back to the main current, and then goes back to the source, to the voltage source, right? And then there is the third loop that actually goes around both resistors, and it's indicated by this green box. the green loop. Right? So there are actually 3 different loops. Those are called voltage junctions, right? But they are essentially just the loops. The behavior or the behavioral current at nodes is governed by the so-called Kirchhoff's current law, or KCL, and the behavior of voltage around the loops is governed by the Kirchhoff's voltage law, or KVL. Both laws are actually consequences of energy conservation. So let's look at Kirchhoff's current law, or KCL, first. Suppose we are at a node with current I1 and I4 flows into the node, and current I2, I3, and I5 flow out of the node. And the voltage at the node is E. So the power that flows into the node is just E times I1 plus E times I4. And the power that flows out of the node is E times I2 plus E times I3 plus E times I5. Right, so for energy to be conserved, the total power flows into the node must equal to the total power flows out of the node. Right? And we can cancel out the E, the voltage E. Right? And then we can move all the currents to the left-hand side. And then the right-hand side becomes 0. Right? So if we assume that the currents flowing into the node, I1 and I4 are positive, and those flowing out of the node are negative, right? Then the summation of the currents with the directions accounted for becomes 0. And this result can actually be generalized to any number of branches. Right? It doesn't have to be just like 5 branches. It can have an arbitrary number of branches. Right? So the Kirchhoff's current law, or KCL, basically says that at a node or at a current junction, the summation of currents from all branches equals to 0 if the directions of the currents are taken into account in the signs of those currents. In practice, the directions of the currents might be unknown at the beginning of the analysis. In this case, we can just assume an arbitrary direction for each current. It is actually remarkable, it's a remarkable fact that no matter what directions are assumed, the final outcome after solving all the equations is always correct. So if you assume a wrong direction for a particular current, suppose you assume I1 to go the other way around, right? The final outcome after the complete analysis will give you a minus sign, right? And that minus sign will automatically correct the wrong direction that you assumed at the beginning of the analysis. Right? That's the KCL. Now let's look at the voltage junction, or the loop, and the Kirchhoff's voltage law, or KVL. Here we have 2 resistors connected in series, and to a voltage source, Vs. Right? Again, we consider energy conservation along the closed loop. So the total energy dissipated must be equal to the total energy supplied. There are no current junctions in this circuit, so the current stays constant. Right? Let's assume it's capital I. Right? So the power dissipated by the 2 resistors is just the current I times E1 plus the current I times E2. Right? And the power supplied by the battery is just the Vs times the current I. Right? And we can cancel out the current I and obtain this relation for the voltage. Right? And we also need to take into account the directions of the voltages. So from high voltage to low voltage, we have a positive voltage change. So E1 is positive, right? Otherwise, we have a negative voltage change. So across this voltage source, the battery, if we sort of follow this kind of a clockwise direction of the loop, right? Then we're actually going from the negative side of the voltage to the positive side of the voltage of the battery, right? So if it's the other way around, from low voltage to positive to high voltage, then we have a negative voltage, right? So again, if we actually try to account for the direction of the voltage, right? After we have accounted for the directions of the voltage by using positive and minus signs, we obtain the Kirchhoff's voltage law, which states that the sum of all voltages or voltage changes around a closed loop must equal to 0. And that's KVL, or Kirchhoff's voltage law. In practice, a realistic circuit can be really complicated, with many different types of components connected in different ways. An effective way for analyzing a very complicated circuit is try to simplify it first. When trying to simplify a circuit, we often need to replace a group of components with one effective component. So the current that flows through this effective component must be identical to the current flowing through this group of components. And the voltage across this effective component must be identical to the voltage across this group of components. This effective component depends upon how the different components in the group are actually connected. There are two basic types of connections: serial connection and parallel connection. If the two components are connected head to tail in a sequence, this is called a serial connection. In a serial connection, the current flowing through each component is identical, but the voltage across each component can be different. So E1 and E2 can be different, right? In this example, we have two resistors connected in serial, right? So the current flowing through both of them is the same, but the voltage across R1, which is E1, can be different from the voltage across R2, which is E2, right? From Ohm's law, we know that E1 equals to I times R1, and E2 equals to I times R2, right? So if the voltage source is Eg, right, then Eg must equal to E1 plus E2, right, which is due to the Kirchhoff's voltage law, or KVL. Right? If the two resistors are connected in parallel, then the current flowing through them can be different. I1 and I2 can be different, right? But the voltage across them are actually identical. So in this example, before and after the branching, the current is I. But inside of the branches, the current flowing through R1 is I1, and the current flowing through R2 is I2. But the voltage across both of them, or across these two black dots, are identical, and both of them equals to Eg. So at the branching point, I equals to I1 plus I2, right? Which is due to the Kirchhoff's current law, or KCL, right? Now let's look at what exactly is the effective component for replacing two resistors connected in serial. Right? So E1 equals to I times R1, and E2 equals to I times R2, which are just the Ohm's law. Right? And then we also have Eg equals to E1 plus E2, which is due to KVL. This is a loop. It's a voltage junction. So KVL applies. So if we bring the expressions for E1 and E2 into this particular summation, what we have obtained is that Eg equals to I times R1 plus I times R2. If we collect the current I, we get Eg equals to I times R1 plus R2. Right. So the effective resistance of the two resistors connected in series can be obtained by dividing the voltage across both of them, that's Eg, by the current flowing through both of them, that's I. And we obtain the effective resistance R equals to R1 plus R2. So if we replace R1 and R2, these two resistors, with a single resistor, with a resistance given by R, we will not disturb the current and the voltage in this entire circuit. In fact, this result can be generalized to impedance. The effective impedance of a group of components connected in series is just the summation of the impedance of each individual component. Right. Now let's look at the effective component for replacing two resistors connected in parallel. Right. Because the voltage across both R1 and R2 is Eg. Right. So Eg equals to I1 times R1, and Eg also equals to I2 times R2, these two equations are due to KVL because this is a loop, right? And then this is another loop, right? So along these two loops, KVL applies. The source has a voltage of Eg, right? And then the voltage across these two resistances are just I1 times R1 and I2 times R2. And the summation of the voltages, taking into account the sign, right, must equal to 0 around a loop. And at the current junctions, at the two current junctions, we have I equals to I1 plus I2, which are due to KCL. The current I1, so the current I1 equals to what? I1 equals to Eg divided by R1, and the current I2 equals to Eg divided by R2, right? So we can bring those two representations of I1 and I2 into this summation. So what we have obtained is that the current I in the main branch equals to Eg divided by R1 plus Eg divided by R2, and we can collect the Eg. So I equals to Eg times 1 over R1 plus 1 over R2. Right. And at this point, if we divide Eg on both sides of the equation, what we obtain is that I over Eg equals to 1 over R1 plus 1 over R2. Right. We know that voltage over current is resistance, right, or impedance. Right? But now it's a current over voltage. It's exactly the inverse of the effective resistance, right? So it's 1 over R, R being the effective resistance, right? It's not it's not R, it's 1 over R because we are dividing the current by voltage. It's not dividing voltage by current. Right? So 1 over resistance is the effective resistance equals to 1 over R1 plus 1 over R2. And this result can also be generalized to impedance and to an arbitrary number of components connected in parallel. And the inverse of impedance is called the admittance. So for a group of components connected in parallel, the admittance of the effective component equals to the summation of the admittance of individual components inside of this group.